So actually, a lot of chemical industry is the process is involved boiling. Okay, and then boiling liquid is usually contained in a vessel with a heating surface of vertically horizontal tubes or plates which supply for the heating and boiling. Like you boil a water in the kettle, okay, and then like the saucepan that you do cooking in the kitchen, okay. So or you have container that you boil the soap in the kitchen, okay. There's a heat supply from the bottom of the pan or from the bottom of the container, okay. In boiling, the temperature of the liquids is the boiling point of that liquid at the pressure in the equipment, okay, and the what pressure, okay, the boiling temperature. So bubble and vapors are generated at the heater's surface and rise through the mass of liquid, like you are cooking mee, the instant noodles, okay, in the kitchen. So of course you have to boil the water first, okay, then you put your meat in, okay. So it's a kind of boiling when you see the bubble slowly rising up, okay. And vapor accumulates in the vapor space above the liquid and is returned when you cover with the lid, okay, of your boiling tools, okay. Boiling and condensation are considered to be forms of convection heat transfer since it involves fluid motion, rise of the bubble to the top and the flow of condensate to the bottom. So it's moving. Okay, the fluid is moving on the surface. So they are differ from other forms of convection in that depends on the latent heat of vaporization. So the difference is the term latent heat of vaporization is there in your boiling and condensation. Okay. And the surface tensions of the liquid vapor interface. So there's a new terms over here. Later on, when I introduce the equation to all of you, then you will know. Okay, so what kind of parameters is needed for the calculations of the boiling rate of heat transfer as well as condensation. So this sigma is not sigma Stephen Boltzmann constant, no. Okay, in boiling chapter, this sigma is called surface tension. It has its own unit and value depending on the type of the surface that you use for the boiling process. Okay, heat transfer coefficient H associated with boiling and condensation are typically much higher than those encountered in the form of conventional process that involve a single phase. So there's a change phase over here because it's involved the latent heat. That's why it's higher. Okay, so you can differentiate between evaporation and boiling by looking at this figure. Okay, so this is evaporations. It happens between the liquid vapor interface. Okay, all right, and then boiling is a solid and liquid. So heating is provided here at the bottom. Okay, maybe it's a circular kind of boiling kettle. Okay, you use gas to do the boiling and water. So it's a solid liquid. Solid is the bottom that provide the heat. The heat transfer is happened over here from the bottom to the water. So we call this one as boiling. This is evaporation. So this is how these two are differentiate among each another. Okay. So just see, this is boiling is solid liquid interface. Evaporation is liquid vapor interface. Okay. So this is the one. Okay. When there's a boiling happen, you have the heating element over here. Okay. Like kettle, you have some stainless steel coil, isn't it? Or any other material making of the coil that provide the heating to the water or any fluid. Okay. So this equation is very important to calculate the heat flux. Okay, I change the color of my pen. So Q boiling. Okay, it's a flux. That's why it's having the watt per meter square unit. Okay, so boiling heat flux from a solid surface to the liquid. Okay, whereby let's say you're boiling water, T saturation and atmospheric pressure, of course, is 100 degrees C. Boiling temperature of the water. So the heating element, of course, it will be having higher temperature with the compared to the liquid. And then you can see the equation is having H Ts minus Ts, and it is equals to H delta Ts. So this will be the new term, delta TSS. Delta TSS is the difference between the temperature of the surface temperature of the heating element and also the saturation temperature. For this case, the TSS over here would be, or delta TSS would be 110 minus 100 degrees C equals to 10 degrees C. Okay, so this is how to calculate the delta TSS. Okay, so simple and straightforward. All right. Okay, classification of boiling, we have two types. The first one is pool boiling. Okay, so the specification is under pool boiling, it is actually happened in the absence of spark flood flow, meaning that it's similar like it's happened naturally. Okay, any motion of the flood due to the natural convection current and the motion of a bubble under influence of buoyancy only. So we call it as a pool boiling. On the other hand, we have full boiling. Full boiling is in the presence of the spark flood flow, meaning that the flood is forced to move in the heater pipe or over the surface by external means, like what you have learned in the external force convection. It's called full boiling. You have external means to pump the liquid, okay, to flow through the pipe. Okay. So our syllabus is only for pool boiling. We are not go for flow boiling. Okay. So our syllabus is pool boiling. Okay. So that's the difference. Pool boiling, like you are boiling, doing some boiling in your kitchen. Okay. And then this is flow boiling, whereby you have the external mean to push the fluid flowing through, and then you have the heated surface. Okay. And we have sub-cold boiling, okay, when the temperature of the main body of the liquid is below the saturation temperature. And then saturated boiling is when the temperature of the liquid is equal to the saturation temperature. This is another type of boiling, but we are actually focused on pool boiling only. So the boiling curve is also under the pool boiling. Okay. All right. So this is sub-cool boiling. And then this is saturated boiling. So you can see the temperature here, the difference, how they categorize. Okay. Yeah, we move to pool boiling. In pool boiling, the flood is not forced to flow by a mover such as pump. Any motion of the flood is due to the natural convection current and motion of bubbles under the influence of buoyancy as defined earlier in the previous slide. Again, it call out this one equation. Okay, so it will be the equation used to determine the boiling heat flux, okay, under different regions in the boiling curve. Okay, so let us move. Okay, so in the boiling curve or under pool boiling, we have four regions. So you can see boiling regions in pool boiling. Okay, started with the natural convection boiling. You can keep on checking the delta TSS because it will categorize the pool boiling region. So the difference is not much. Started with the natural convection boiling, and then when the difference is getting larger, so it will proceed to nucleic boiling. Then after that, transition boiling, and finally, flame boiling. So these are the four regions under pool boiling. And it's shown in the boiling curve. Okay. Let us see the boiling curve. Don't be afraid, students. This boiling curve is actually quite clear. Okay. Let me explain to you all. As I mentioned just now, there are total four types of boiling regions in the boiling curve. Natural, nucleic, transition, and flame boiling. You can see the heat flux, y-axis, started to increase. Okay, and reach maximum, we call it as a critical heat flux, and slowly reduce the heat flux. So at the latent frost point, Q mean, and then when it's reached the lowest point, is increased back under flame boiling. Okay, so you can see natural nucleic transition and flame boiling. Point A and C is still categorized under nucleic boiling. Okay, transition is from maximum to minimum heat flux, and slowly flame boiling. Okay, so let us look at the x-axis. How I can categorize this range is based on the delta TSS. Okay, the real value over here doesn't matter. The important is this value. Very important. Okay, you can see it falls under natural convection when the delta TSS is between 1 to 5. Okay, delta TSS is what? The surface temperature of the heating element minus the saturation temperature of that fluid, boiling fluid. Okay, then after that, under nucleic boiling, you can see the range is from 5 to 30, isn't it? Okay, delta TSS, if it is falls between 5 to 30, it categorized under nucleic boiling. Okay, so what happened? It has two regions, 5 to 10 and 10 to 30. Don't worry, all also under nucleic boiling. Just the bubble is not um uh it's not the same. So from 5 to 10, the bubble collapse in the liquid. And from 10 to 30, the bubble rise to the free surface. So that's only the difference. Okay, the motion of the bubble. Okay. After that, it will reach the maximum here, right? So it called critical heat flux or maximum heat flux, but it still fall under the nucleic boiling range. What happened over here? Okay, from the maximum to minimum. So you can see the delta TSS is within 30 to 120. Under this transition range, there will be a Qmax and Qmin happened here. Okay, so how would be like the boiling liquid? It You can see the vapor pockets start to form. Okay, vapor pocket, and you can see why the heat flux is reduced, but the delta TSS is actually higher than that in the nucleic and natural convection boiling, because this vapor pocket will form as an extra resistant. That's why you can see the Q boiling, okay, the heat flux, boiling heat flux is actually reducing, because when there's a much more vapor pocket form here, it will create extra resistance for the heat transfer process. So Q boiling is actually reduced. So after it's reached the Q minimum, when the delta TSS is larger than 120, so it start increasing back. Because don't forget Q boiling is equals to H delta TSS. Right now, delta TSS become increase, then here also increase. So you can see in the flame boiling, there's a vapor film already formed over here. And then the temperature difference is actually quite large. Okay, so it's fall under flame boiling. If it is larger than 120, it will become flame boiling. Okay, so this is the pool boiling mechanism. Okay, at different delta TSS. Okay, so you can see how does the liquid behave in each of this region. Okay, any questions, students? Is that clear for the boiling curve? For the boiling curve, any questions? Any questions before I proceed? Don't worry, the following slide is just to recap again this boiling curve, okay, for each of this region. Okay, so yeah, it started with the natural convection boiling here. Okay, just now I do an overall explanation on this boiling curve. Right now, the slide itself is mentioned more detail, discuss more details, what would be there in each of the region. So started with the first region, the natural convection from to point A on the boiling curve. Bubble do not form on the heating surface until the liquid is heated a few degrees above the saturation temperature. So the heat transfer process is by natural convection. Natural convection boiling end at an excess temperature of 5 degrees C. So it will be ended over here. So you can see there's no bubble form. Okay, no bubble form, started to boil only. Okay, all right. And then after that, nucleic boiling between A to C. Okay, the bubble forms at an increasing rate at an increasing number of nucleation sites as we move along the boiling curve towards the sea. So you can see more bubbles form. You can see the pictures. Okay, so bubbles start to form, and then here bubbles start to rise. Okay, and then you can see the type of bubble. A and B is isolated bubble. B and C is continuous column of vapor in the liquid. Okay, so the heat flux at point C is called critical or maximum heat flux over here. So the whole boiling region, the delta T excess would be 5 to 30 degrees C. Okay, that's all for the nucleic boiling. Okay, and until its maximum point. So transition boiling, okay, when delta T excess is increased past point C, the heat flux decrease. This is because a large fraction of the heated surface is covered by a vapor film, which acts as an insulator. This one is explained. Okay, why it is decreasing. In the transition boiling region, both nucleic and film boiling partially happen. So it's called transition. So it's still a partially nucleic and a partially film boiling. For water, transition boiling occurs over the excess temperature range 30 to about. Because this boiling curve is belong to water. Okay, so it's about 30 to 120. Okay. Finally, it's reached boiling, film boiling. Beyond point D, the heated surface is completely covered by continuous stable vapor film. Okay, all right. So the presence of vapor film between the heated surface and the liquid is responsible for the low heat transfer rate in the film boiling region. So it's still low starting here. Then after that, it slowly increases. So minimum point is called latent force point. Okay, kill me. All right. So this is explained as a recap also for you all. Okay, started with the first boiling curve. Okay, and then explain one section by section. Okay, so this is the summary. Okay, so summary, you have natural, nucleic, critical heat flux, minimum, and film boiling. Okay, boiling region different considerably in their character, and different heat transfer relation need to be used for different boiling region. This is our ultimate goal. Why? Maybe you ask me, why I want to know each of these region? Why? What is the purpose? Because different heat transfer relation need to be used for different boiling region because their behavior is not the same. That's why correlation also not be the same. Okay. In the natural convection boiling region, heat transfer rate can be accurately determined using natural convection relation. Okay, so here for the natural one, so doesn't matter, you have already known it. Okay, the natural convection kind of calculation. Okay, all right, so it's under chapter 7, 8, and 9 here. All right, so yeah, after knowing the theory, as I mentioned, Why you want to know each of this region? Because each of this region will have different coloration. We will be started with the nucleic boiling because this one can be determined by using the nature convection relation. Okay, so in the following slide, you will recognize first what is nucleic boiling coloration, what is the coloration used for critical heat flux, what is the coloration used for the minimum heat flux, as well as the film boiling. Okay, so started with the nucleic boiling. Wow. So this will be the equation. Okay, don't copy wrongly, students. It's used to copy wrongly from the slides or from the lecture notes when you're answering the questions. This author not new to you all, okay? Just the subscript like mu L. When you look at the water, you have the liquid and vapor phase, isn't it? It's the viscosity of the liquid. HFG is the new term, it must be here. That's why the Q nucleic or the Q boiling is higher. It's explained in the previous slides, in the introduction slide. Enthalpy of vaporization. Gravitational acceleration G is not new to you all because you are using it in the nature convection as well. Okay, it's 9.81. Raw L density of the liquid, raw V density of the vapor. Again, this one, surface tension of the liquid vapor interface. So it's not the 5.67. It's not Stephen Boltzmann constant, student. No. Okay, it's not that. Okay. CPL is a specific heat of the liquid. Ts is the surface temperature of the heater. T saturation is the saturation temperature of the fluid. Have a new constant over here. We call it as an experimental constant, depends on the surface liquid combination. So this one is new. Okay. Prandtl number of the liquid, not new to you all. And then you can see, I need to clear. This one small letter of N. Experimental constant that depends on the fluid. So all these parameters can be determined from the properties table except the one that I circle, the three. Sigma, surface tension of the liquid vapor interface. Okay. CSF, experimental constant, depends on the surface liquid combination. And the N value here, experimental constant that depends on the fluid. All the properties are to be evaluated at the T saturation, student. So you have to know the T saturations of the liquid. Then you get all these parameters. Okay. Right now we move how to get these three. Okay. We go to the next slides. Okay. This one, I purposely put it here to show that, okay, this is raw L, and then this is raw V, isn't it? Okay, this is HFG, and then this is the saturation pressure and temperature, and then also you have this one mu L, and then this is mu V. Okay, all are here. Okay, all properties are here. Yeah, this is the one. This is the sigma value, depends on the T saturation. This is T saturation. If lesser is 100, then the sigma value is 0.05894 for water. Of course, you have the other fluids. They have some correlation here to calculate. Okay. So depending on what type of fluid. Okay, water is always this one. If the saturation temperature is 100. Okay. So this is how you get the sigma value. This is sigma value. Okay. This is sigma value. Then CSF and N. Yeah, this one. Meaning that for nucleic boiling, you need to have few tables to radiate properties of water or the liquid, the surface tension table, and also the coefficients and N values table. So that's why you see the heating plate is very important. The material make of that particular heating plate is important. You need to know whether it's a copper or stainless steel or brass or nickel. Okay. So usually you see For copper, it divided into polish or score. For stainless steel, it will be divided into mechanical polish or ground and polish or Teflon bit or chemically etched because they have different combination of CSF and N value. Okay, so student, bear in mind, the question is always asking. Okay, I give you an example first before we go to the other equation. You see, usually it will mention mechanically polished stainless steel pan. So meaning that you need to know here mechanically polished. Then from here, I will automatically pick up this two, 0.013 and n value equals to 1. Because it's mentioned in the question mechanically polished. If the question is saying ground and polish, then you need to take this value already. Okay. All right. So three tables are important under nucleic boiling. The first one will be the properties table. So all the properties will be evaluated at T saturation. Okay. Followed by the surface tensions. You need to get the sigma value. It's not the Stephen Boltzmann constant, but it's the surface tension of liquid vapor interface. Okay. Then after that, you need to know the CSF and N value for different combination of fluid and the heating surface. Okay, heating surface. Okay, that's all for the nucleic equation. Right, we are settled the nucleic side. Nucleic boiling here done already. Then we right now move to the critical heat flux. So another equations over here for critical heat flux. So this is the equation used. So CCR is the new term. These all are the terms that I have been introduced just now. Okay, so raw V, raw L, G, sigma. Here CCR. It's not CSF. CSF is different. This is CSF. But under heat flux, peak heat flux, or critical heat flux, they are the same. Sometimes the question will say that critical heat flux, and sometimes we'll call it as a maximum heat flux, or sometimes it will call it as a peak heat flux. They are the same. Okay. So right now you need to know how to get the CCR. Okay, CCR is a constant whereby the value depend on the heater geometric. Still the heater again. Okay. So heater, there are many types. Whether it's a horizontal or there's a spherical heater, whether it's a flat one or cylinder type, whether it's a small one or large one. Okay, so there are different CCR value over here. You do not know which one to pick up. So definitely the very first step that you need to know is you know that this is a flat like a pan. Okay, if it's a flat or the heating is like a coil or wire type of heating element, that it will fall under cylinder shape, and this one will fall under the flat. Spherical object is okay. All right. But you have large and small term over here. You do not know which one to be used, isn't it? Don't worry, student. You can see this is the one that you need to determine first. You need to know the range, L asterisk. L asterisk is represented by this equation. Okay? So you will get the L value over here. Okay? So if it is a flat heater, you will use the width or diameter. If it is a horizontal, you need to use the radius to substitute in this equation first. If the L set, if you found out that this is the flat heater and you found out that the L asterisk is more than 27, then your CCR will be 0.149. This is how we get the CCR value. Meaning that first thing you need to know is you need to know the heater geometric, whether it's a flat one or cylinder type. The second one, you need to calculate the L asterisk because I do not know whether it's a small or large. Okay, I do not know whether it is small or large. So I need to prove this L asterisk. If it is larger than 27, meaning that it's a large horizontal flat plate, and I straight away use 0.149, the CCR. Okay, the L value is shown here. Either you are using diameter, width, or radius for different kind of heater. Okay. So right now you just recognize and know the equation first. So the next class will be utilizing of these equations. Okay. So the next one will be the minimum heat flux. Again, the nucleic boiling, peak heat flux and minimum heat flux, all the property will be evaluated at T saturation. So Q mean is very easy, you see, just the raw L, raw V, and sigma value. It do not have extra parameters like CCR for the heat peak heat heat peak heat flux, and then also it doesn't have like uh, the CSF and N value for the nucleic boiling. Okay, it's only have the sigma value for the Q mean. Okay, all right. So that's all about the nucleic max and minimum heat flux. So we have remaining 6 minutes over here. I think I just introduced this film boiling to all of you. Okay, so there are total 4 equations: nucleic boiling or nucleic heat flux, maximum heat flux, minimum heat flux, and Q film, film heat flux in the boiling curve. Okay, that's all that you need to recognize. Only 4 equations. But of course, you need to know. You do not know which, the question is talking about which region. The best way to determine the region is to calculate the delta TSS, isn't it? So meaning that if the delta TSS is within 5 to 30, it's definitely nucleic already. Okay, so on and so forth. If it is more than 120, yeah, falls under Q firm boiling region, some sort like that. This is the best way to categorize the flow region, okay, or the boiling region. Okay, so this is the equation, a long equation, okay, more complicated than those in the in the convection, but it's actually just to substitute the value in it. Nothing difficult over here for the boiling and condensation. Once you identify the boiling region, you can easily call out the equation and then put all the value in. That's it. Make sure all the value here are under the SI unit, meaning that kg meter second. Then you can get the answer straight away. Okay. If you still get the wrong answer, meaning that your calculation wrong. Okay. So it's C film. So all this is already you known. Okay, all this parameter is already defined in the previous equations. Only the C film here, 0.62 for horizontal cylinder, 0.67 for spherical. Okay, all right, so to get the C film. But students, this is very important. For the nucleic maximum and minimum heat flux, you need to refer to the T saturation. Haha. For Q film, no. More complicated. But you can always refer to the slide, no problem. The vapor properties are to be evaluated at flame temperature. Is Ts plus Tz divided by 2. The liquid property and HFG are to be evaluated at T saturation, meaning that you need to refer to 2 different temperatures to get the properties. You need to refer to saturation temperature to get the liquid property. Let us see where are the liquid property. Only this one, raw L. Okay, raw L. The rest subscript is the V. Vapor property will be evaluated at flame temperature, whereby flame temperature is the average of the surface temperature of the heating element plus the saturation temperature. Okay, is that clear, student? So meaning that raw L and also HFG will be evaluated at T saturation for firm boiling. The rest, nucleic boiling, max and min heat flux, okay, all using TZ only, T saturation only. Only for firm boiling, you have 2 temperatures to be referred to. Okay? So this is the Weber film. You can see the Weber film form here. The difference is 300. Okay, we have extra film over extra considerations over here. A high surface temperature, if it is above 300, heat transfer across the Weber film by radiation becomes significant and need to be considered. And treating the Weber film as a transparent medium sandwiched between two large parallel plates and approximating the liquid as a black body, radiation heat transfer can be representing by equation 10(6). Again, this equation is not new to you all. So here, the sigma is Steven Boltzmann, students, no longer surface tension. But this equation is only applicable for the film boiling. Film boiling, when you look at the equation, it doesn't have any sigma value over here. That's why you will not mix up. The sigma value is in the nucleic boiling only, the surface tension. But here under the film boiling, when you see the sigma, it belongs back to the Steven Boltzmann constant. Okay? And then this will be the Q total under film, Q film. Okay, under film boiling. So you need to calculate the Q film by using the previous equation 5. And finally, you need to add on the radiation effect here. Okay, it's plus 3 over 4 Q radiation. Then you will get the Q total. So only a bit more things to consider under film boiling. Okay, whereby you need to refer to two temperatures to get all the parameters ready. And also you need to consider the radiation because you can treat it as a large parallel film. There will be a Q from the radiation as well. Okay? All right, students, that's all about the theory under boiling. So meanings that you need to know pool boiling, you need to understand the boiling curve. Okay, you need to know how this boiling region categorized under the boiling curve. And also finally, you know each of this region will have different correlation to calculate the Q boiling. Okay. And then let's say the boiling is falls under the nucleic boiling. You need to use what equation? Okay. Q max, Q means Q nucleic, Q max, Q mean you only need to refer to one temperature for to getting all those property, which is T saturation. For Q film, they are a bit more complicated. You need to refer to two temperatures. One is the film temperature between the surface temperature and the saturation temperature for all the vapor properties. And for liquid property, raw L and HFG, the latent heat of vaporization, you need to get it from the T saturation. And finally, under film boiling as well, you need to consider the radiation effect and you have the Q total. Okay, you have the Q total before you proceed on to calculate